Okay, let's begin. So welcome to day 3 of this Agda course. So what we did on Wednesday was we took unchecked lambda terms and we wrote a parser, a type checker that returned a well-typed lambda term. So today what I hope to do is actually run these lambda terms. And you might have in the exercises written the evaluator for the well-typed terms. Today we're going to run them through the SCCD machine. So what I did was I looked up this paper by Olivier Danvy, where he describes, in a more accessible way the SCCD machine than if you look in the original paper. And then I basically just copied the definition into this Agda file. So that's where we're going to start. So if you want to follow along, this file is under exercises SCCD unchecked.agda. So let's just walk through it. I mean, not everyone, I'm sure, is familiar with the SCCD machine. So it's called the SCCD machine because there are four things. It's the stack, the environment, the control, and the dump. And let me go through what those things are. So first of all, we're going to need a notion of values. So we're going to run the SCCD machine, and in the end, we hope to get out a value of some kind. So for our lambda terms, the values are either literal natural numbers, so it's just a nat. It's successor, so the successor function, or it's a closure. And a closure takes, the name of the variable that you don't have yet, an environment with values for all the variables that you do have, and then the term that needs the value of this first variable in order to be able to run, and that's the value. So it's basically what's a closure? Well, it's a lambda and an environment tacked on. And then so the environment component of the SCCD machine, as you see, is defined up here, is a list of name value pairs. So it's a mapping from variable name to values. So that's what the E is.
Could you explain the syntax? So you use value there and...
Oh yes, so this is a syntax for mutually recursive things. So you'll notice here a value has an env in it, and an env has a value. Now I could have inlined, and I could have typed list name cross value in the definition of the data type, and everything would have been fine. But then I would have to repeat that when I define env. So if you want to have mutual recursion in Agda, you do what you do in C, right? You write the type signature first, so that everything you're using has a type signature before you're using it. And type signatures for data types look a bit funky. You still say data value of type set, and then later on when you define it, you don't give the type, you just say data value where. But basically, the idea for mutual recursion is you just write the type signature before you need to use the function. Okay, so that was the E. So the S, it's the stack. So it's where you put the results of intermediate computations. And so in this unchecked version, we're just going to use a list of values. So the stack is just a list of values, what you would expect. The control part is where the program lives. and it's a bit more interesting, the C. So it's in this version, it's a list of directives where a directive is either just the term that we want to run, or it says, take whatever's on the stack and apply one thing to the other and put the result back onto the stack. So the idea with a term, when you have a term as the first thing in the control, then you want to run that term and put the value you get by running it on top of the stack. That's what you hope to do in the machine. And apply then, expects a function and a value on the stack, and then it's going to apply the function to the value and put the result onto the stack. Okay, so then the last thing is the dump, which is where you put things, when you have to do a context switch, you put the current context onto the dump, and then you go do some other things. And in particular, when this comes into play when you're going to apply a closure to a value, right? But then the closure has its own environment. And so you need to swap out your environment, put in the environment for the closure, run the computation, but then you'd better not lose your own environment, because then you're going to get back a result and use that to do some further computation. So what you do in that case, as we'll see in the definition, you just take whatever you have at the moment, put it on the dump, swap in the stuff from the closure, and run that computation. And when that finishes, you pop back your own context from the dump. So on the dump, in this formulation, we're basically putting everything we have at the moment, we're just sticking on the dump. So it has a stack, an environment, and a control is what you put on the dump. So that's called a snapshot here. So it's a snapshot of the current state of the machine, and the dump is a list of snapshots. And then the final SCCD configuration, since I defined a data type, or a record in this case, which I'll explain in a second, for snapshots, well, the SCCD machine is just, the current snapshots are the S, the E, and the C, and then the list of things we put off until later on the dump. So the record, hopefully you can kind of read this. So it defines a record with, if you take the snapshot, it has 3 fields. So it's a record type. You have a field stack, field environment, and a field control. Behind the scenes, what this really means is just it defines a data type with a single constructor. And then you have some eta properties about it, which is not going to be important for this. But you can think of the record as just defining a data type with one constructor that I've named in this case. I've named it snapshot. And this constructor has 3 arguments: stack, env, and control. And then what the record definition does for you, it defines the projection functions from this data type. But actually, we're not going to use the record facilities at all. We're just going to treat it as a data type. Which one?
Open snapshot, what does that mean?
It means re-export. So you have the field name stack, environment, and control up in snapshot. And when I say open snapshot current, it means take this snapshot here and expose the field names as if they were fields in this record. And then public just means when you open, when you look at an SCCD thing, these will be, the stack environment and control will be available as projection functions directly from an SCCD.
So it's whenever you're in the scope of a variable of type, of the record type, it will let you refer to the fields directly. Is that the idea?
Well, not quite. So what you get is, when you declare a record, you get the projection functions live in a module with the same name as the record. So basically, up here, I can ask, what's the type of snapshot.stack? And that's the projection function that takes a snapshot and gives me a stack. But what this lets me do is it gives me also SCCD.stack, which is a function from SCCD.stack, which just goes through the current. Sorry? Yeah. So it gets baked into the SCCD. I don't think I'm actually going to use the projections. I'm pretty sure we're not. So we're just going to pattern match, treat them as data types and pattern match on them. And in fact, I'm going to define a little pattern synonym to make it look like we just have a for tuple, like in the original formulation. So when I say S bar E bar C bar D, then what I really mean is the SCCD configuration. This is the current snapshot, and there's the dump. And these are Unicode bars. I'm sorry, because the bar is reserved. So. And comma comma would have been nice, but that's for pairs, so it wouldn't parse that. If you have a better separator, please tell me. Sorry? No, that's the thing, right? And then the bar is, it's fine. It's \bar, so it's not horrible to type. Okay, so then let's move on to actually, defining the actual machine. So we've set up, what is the configuration, and I've talked a bit about what the different things are for. So first, let's define, what should this, and it's an abstract machine, so we're going to define a step function that takes a machine configuration and does one step. And what does it mean to do one step? Well, there are a few things that could happen. We could, be finished. So I define a data type step result. So there's one constructor done, which just says, okay, the machine has stopped. Here's your value. Or it takes one step and gives me the next configuration. So that's next. Or something went wrong. So we're running unchecked terms here, so there are many things that could go wrong. You could refer to a variable that's not in scope, and then there's nothing the machine could do. So we have this error result as well, and then a helpful string saying why the machine crashed. So let's look at that. So the first case, pull this up. And then this is pretty much out of the paper. You just read the paper and then you transcribe the rules pretty much as is. So in the first case there, when we return done, so we have, there's nothing on the control. So there's nothing left to do. There's nothing on the dump, so there's nothing we've put off until later that we could sort of bring back now. And the stack has exactly one element v. That's the win condition for this little game. So then we say, okay, we're done. Here's your value. It's v. So the other case, when the control is empty, the second case here, so there's nothing left to do on this thing, but we had some stuff that we had to do, that we put off. And so let's do that now. So it says, there's nothing on the control, but we have some snapshot on the dump. So let's pull that back in. So notice this E prime here we don't care about. There's nothing left to do here, so the current environment is, we can throw that out. But we computed a result, V. And that's exactly what this snapshot wanted. So when we're going to get down to when we actually take the snapshot, it wants another thing on the stack to be able to continue. And so we put the V onto the stack we had in the snapshot and just let that run. So we install the environment from the snapshot, the control from the snapshot.
So this pattern expression works both on the left and the right side, right?
I'm sorry?
So you use this bars from pattern expression, so you use them as a function, right?
Well, so when you define a pattern synonym, you can use it both on the left and the right-hand side. So I'm pattern matching on the configuration using the bars, and then I return a new configuration also using the same syntax. Those we don't need. And there are various ways. You could maybe not put the stack in the snapshot and just leave it as the stack, and then you wouldn't have to do anything in this case. So there are various variants you can do, but this is straight out of the paper. Okay, so that's when the control component is empty. What about when it's not empty? Well, we might have a term, and it might be the term just the number n. So what was the purpose when we had a term on the control? Well, the idea was that we should run some computations, and then in the end, the value of that term should end up on top of the stack. And in this case, the term is a number, so that's the value. There's nothing we have to do, so we just put that on top of the stack, and we're good. Same for a variable. The variable, we just look it up in the environment, which has a value, hopefully, for that variable. So we run a lookup function that looks up x in E, and maybe it finds it, maybe it doesn't. So if it doesn't find it, that's an error case. If it does find it, well then, that's the value for this term, so we just stick that onto the stack, and we're good. The same for, where did we go now? The same for successor. Well, successor is a value already, so we can stick that onto the stack, no problem. Lambdas are kind of values, but we have to build a closure. So if we see a lambda, we stick a closure onto the stack where we remember the current environment. So we stuff the current environment into the closure. So that later on down here, when we apply it, we can plug that environment in for the current environment. Application is easy. We just expand that into three things on the control. So to run an application, well, first you run the argument, put that on the stack, then you run the function, put that on the stack, and then you do an application of the top element on the stack to the next element on the stack. So that leaves us with the application cases. So the simple one is when you apply successor to a literal number. Well, then that's just you put the natural number successor. Let me make this more clear. So that's you put the actual natural number n plus 1 onto the stack. And then we have this interesting case where you apply a closure to an argument. And that's where you have to take a snapshot of the current state, so that once you've finished this application and you've got the result, you can keep going with C here in the current environment, because to run the closure, we have to use the environment in the closure. So what does it do? We take the stack, put it in the snapshot. We install the environment E prime from the closure with the extra binding for X that we have sitting on the stack there. And then the program we run on the control is just the term from the closure. And then on the dump, we just put all of the current stuff. Okay? And then there are a bunch of other cases. So if you just wrote down these, and these are of course the ones that are in the paper. Agda would say, well, what about this case? What if the stack is empty and the control is empty? You don't have a case for that, and we don't. And so we have to add an error case saying, well, there was an error. We finished the program and there's nothing on the stack. Or there are too many things on the stack, or you try to apply but there's nothing on the stack, or there's just one thing on the stack, or you try to apply but then there's a number sitting on the stack and not a function. So these are all well, yeah, okay. So there are two things here, right? So right now we're running unchecked terms, right? So this case is perfectly possible. I mean, I could write an unchecked lambda term which tries to apply 1 to 0, and we'll end up in this case. And there are the other cases up here. They are actually impossible even with unchecked terms. These are the stack errors, and if you would study the definition up here closely, you could sort of figure out that they can't actually happen. And so that's going to be the next thing we're going to do, is we're going to explain to Agda that these guys can't actually happen, and then hopefully we can get rid of those cases. Okay, so first let's tie things together. So we want to run these, of course. Yeah, we've got the lambda term, we've got the SCCD machine. I don't want to step through. I want to run it and see what comes out in the end. But of course, unchecked terms, they're not going to. I can easily write a non-terminating lambda term, and then the program is not going to terminate. But I don't really care. If you write a non-terminating lambda term, well then don't run it, or run it and then hit Control C when it doesn't come back. So I just say, well, yeah, this isn't going to, no, in this case, it really isn't going to terminate for some lambda terms. So the termination checker is justified in saying there's a problem here. But I just say, well, don't worry about it. So that's in the spirit of what we're doing here. I want to write a program. Some things we're going to get, some guarantees. Some other things we're not going to bother proving that everything is perfectly correct. So I just turn off the termination checker here and say, how do you run an SECD machine? Well, you take one step. If that says next S prime, well, then you just keep going. If it's done, well, then we're done. If it's an error, it's an error. And then the top level thing takes a term and builds the initial configuration, which is empty stack, empty environment, just a term on the control. And then the idea is that this should then put the value of the term on top of the stack. So what this does, though, when I say no termination check, it means that the type checker is going to be very reluctant to evaluate this function. So if I try to use this in a type somewhere, it's not going to reduce, right? Because the type checker is going to go, well, no, I don't want to touch this. You told me not to termination check it, so I didn't. But then I am also not going to run it because I don't want to diverge. But if we're just compiling and running, then it's fine. So let's do an example. So here's the function that takes a string, parses it, and then runs the result. So we can run unchecked, I don't know, lambda, x in nat to successor of x applied to 15. And it runs and it comes back 16. Okay? Any questions on this bit so far? So I think in your files, this guy is defined in lambda.agda, and I just moved it here to be able to run it. So I didn't have to swap buffers.
Where does the parse term come from?
So that's in term.parse in this module here.
Oh, I see. It wasn't in the source code.
No. Okay, so that was the boring, untyped, well, not untyped, but boringly typed SECD machine. And it was okay, I guess, but we had these. It wasn't like in the evaluator we did on the first day where it just got completely messy. This was okay, but we had these annoying, error cases down here that they shouldn't happen. So why do we have to write them out? So let's try to fix that. So we're going to start with the stack discipline. So the errors that even on unchecked terms should never ever happen. We shouldn't run out of stack because the way we're running these things, we always the stack is always well formed. So what do we have to do Well, we're going to, at the very least, we're going to have to keep track of how many elements are on the stack, right? That's the minimum thing we have to do. So let's do that. So right now, stack is defined as a list of values. Well, that's not going to be quite enough. We're going to need to have lists that also carries some information about the length. So in the libraries, there's a type vec, which is just that. So instead of a stack being a list of values, it's going to be a vector of values. And well, okay, let me write this out to make it clear. So vector takes an extra length argument, which is the length of the list. So then we're going to need, to keep that thing there. Except we don't have an n, so I'm just going to put in an extra field in the record for n. And then I put that in curlies, and this should now type check. It does, good. So I declare a field n in the snapshot record, but I put it in curlies, which means it's an implicit field. And so if you remember, I said, well, records are just single constructor data types, so that just means n is an implicit argument to the snapshot constructor. Which also means that, notice I checked this. All the code we had below the definition of the SCCD machine, that still goes through. It's just, keeping track of the height of the stack everywhere and behind the scenes. Okay, so now we know the height of the stack, but we don't know, how. Yes.
Arguments. So it looks like you can make any argument that you want implicit, right? But
yes.
I suppose you have to be, since n isn't in the type of the record snapshot, you kind of sometimes have to be clever about where you use them. It has to be able to figure out from context.
Well, yeah, so you can make anything implicit, but if it doesn't, that just means you don't write it, and the type checker tries its best to figure out what it should be, but of course it's not always going to manage. Right? And then it's going to color your buffer in yellow and say, oh, no, there are these unsolved implicit arguments that I couldn't figure out what they should be. And then you have to go in and figure out where you left something implicit that really oughtn't have it. Okay? Right, so then, now we know the height of the stack, but we also have to think about how high should it be? Well, it depends, right? It depends on the control. Over here. So let's look at the directive data type. So this is directive that's one element of the control. So we have this term, and when we talked about this, we said, well, the term directive is supposed to put the value of the term on top of the stack. Right. So we really should, not just say that. We should tell the type checker, right? So I'm gonna make directives be indexed not by a single natural number, but by two. So the first one is, I expect this many elements on the stack to begin with, and then after you've finished this directive, there should be this many elements on the stack, or there will be this. So that's Greg. The first one is Greg's precondition, and the second is the post condition. So what about term? Well, the term for any, you can run a term directive on any stack. Right, it doesn't care about the stack in the beginning. But what it does is it puts one extra thing on the stack. What about apply? Well, so what did we do in apply? Well, we expected two things on the stack, and then we wanted to apply one to the other and then put the result on the stack. So there had better be two things at least on the stack, and when we're done, there'll be, we take those out and put one other thing on there. Okay, now we're going to get to type error down here, of course. So a control, what's a control? Well, it's a list of directives. Well, now directive is a more interesting thing, right? It's indexed by starting height and ending height of the stack. So, we can't really use a plain list anymore. So we have to use a fancy list. And some of you, I know, did some exercises on that. So if you did, you'll remember I defined in the exercises, I defined a data type path, which was defined, represents a path in a graph as a list of edges, where the starting nodes and ending nodes match up appropriately. And that's exactly what we need here, right? So let me just do this. Oh, it's not in scope. Yeah, okay, now so let's look at open import lists. So it's in the lists module from the lectures, and it's right here. Yes?
So for apply, it's true for all the easy cases, but for closures, it doesn't take two things off the stack, put one. The next step has an empty stack.
Well, I guess we'll find out, yeah? So we're writing. So we might write down nonsense, of course, in the types, and then the type checker is going to complain when we get to the actual implementation and say, well, you told me there should be n things on the stack, but actually it's empty. So we get an error. So let's come back to that when we get there. But the machine is checking everything we do. So if we make a mistake, it should tell us. Okay, so what's a path? Well, suppose you have a type of edges. So you have a type of nodes, which is I in this case, and then you have a type of edges E. So and Eij is an edge from I to j. Then in a graph like that, you can define the set of paths as just a list of edges, but crucially in the cons case. So the empty list is a path from one node to itself, and a non-empty list, well, you take an edge from I to j, and then you take a path from j to k, and then you get the path from I to k. And so if we think of our directives and the control, so the control is a list of directives, but you start out with a stack of some height, and the first directive gives you a stack of another height, and then the second directive had better accept the new stack height, and then in the end you hope to get down to a stack of some particular height. Okay, so in the snapshot, so any questions about the path type? I might have gone over that a bit quick. No? Okay. So what about this snapshot then? Well, so now control is a path from one stack height to the final stack height, well, what should the initial stack height be? Well, maybe n. And what should the final stack height be? Well, once you've exhausted all of the directives, we're expecting there to be exactly one element on the stack, so this should go down to 1. Okay? Let's try that. Oh. That didn't work. So we got a type error now. And it's saying, so it's in this case here. So we've finished our control, the current control, but there's a snapshot on the stack, and what we want to do is we want to take, the snapshot on the dump and put in the stack and the environment and the control from that snapshot and keep going. But we also added V on top of the stack. And so what the error message is saying, it's basically saying, look here, C in the snapshot has type control n1, so it's something that expects a stack of height n and will go down to a stack of height 1. But you gave it up here a stack of height n plus 1. And that doesn't work. And so actually, if we think about it, this is the correct implementation of the SCCD machine. So we made a mistake in the types. And when you think about it, in the dump, the snapshot, the control in the dump expects one extra thing on the stack. So this definition is fine for the current snapshot. For the current snapshot, we have everything we need on the stack, and we're going to run it down until we have just one thing. But for the things on the dump, there's a thing missing on the stack. So we need to encode that. And I'm going to do that by just parameterizing the snapshot type by how many things are missing from the stack. So we do this. We say, well, the snapshot where j things are missing from the stack, it's a stack of height n, an environment, and then a control which expects j plus n things on the stack, and will go down to 1. So if we do that, then on the dump, all the snapshots expect one more thing. But the current snapshot expects no extra things on the stack. It's got everything. Okay. Well, still errors. Wow, okay. Okay, so what about this one? It's saying 0 is not 1 when checking that some pattern has some type. Wait, this is one of the annoying error cases, right? So what it's saying here is, there's no way this could happen. So why don't we just delete that? I'll run. Okay. This is also not correct. What should we do? Well, we take it out. And okay. More errors. You can't apply. You can't do apply on an empty stack. Well, okay. Let's not. You also can't do apply on a singleton stack. So I guess we won't do that then. And then it checks. So notice what we didn't have to change. I didn't touch a single one of these clauses. Yes, Bob.
You must have done about that little jag, because I
Let me go back.
I get it, unbound that in, sorry, jag. Where did you take it from?
So I'll put it up here. So this really means J all time now.
This is what I mean when I say we should, when programming with dependent types, you should use dependent types to make things nicer, right? And that's exactly what we did here. We put in some types, and the cases we didn't want to talk about went away. Everything else just stayed the same. So there's one little trick that makes this actually work out in practice, and it's the fact that we can overload constructors. Remember we changed the representation of stacks from lists to vectors. Well, down here, we're pattern matching on stacks, and so if we'd had a different constructor name, a different cons for vectors and for lists, then we would have to go over this and rename list cons to vec cons, and it would have been annoying. But since we can use the same names, and the type checker will just figure out which one you meant, we didn't have to do anything else. Okay. Oh, to come back to your question, it never came up, right? So it must have been okay. Let's figure out why. Let's figure out why. I mean, okay, the type checker figured out why, but maybe it'd be instructive for us to also understand what happened. So the case you were worried about was this case, yeah, where we're applying a closure and then we stick the empty stack onto the current snapshot. But remember, the height of the stack is existentially quantified in the configuration. So you could as long as you build a well-formed, we can give back any configuration here as long as it's well-formed. And so, yes, we're starting with a configuration where the stack height is some n, well, n plus 2 actually. And then we take one step to a configuration where the stack is empty. But that's fine as long as we maintain the invariance between the control and the stack. We don't actually care about the height of the stack other than that it should match up with whatever you have on the control. Right. Yes.
Make sure I understand that correctly. During our computation, we have an empty stack, provided that there's still a path from the empty stack to a final state.
Yeah. And I mean, we are, in that case we just looked at, we do run with an empty stack. The types guarantee that whatever we do in the control is going to put enough stuff on the stack so that in the end we end up with a single line.
Okay. So that got rid of some of the error cases, but not all of them. So let's see if we can get the remaining ones. So if we look at those, what are the cases that where we still return an error? Well, it's this one where we have a variable that's out of scope, and then it's these ones where we apply a number to some argument, we apply successor to itself, or we apply successor to a closure. And those are really type errors, right? And now we're running on unchecked terms, so of course, there could be type errors. But we just wrote a type checker that computes well-typed terms. So why don't we just run well-typed terms instead, and then everything will be fine, yeah? Well, I guess we'll find out. Okay, so what do we have to do? Well, we should change unchecked here to well-typed. That's going to give us back some errors. In particular, this one that says, well, term is not, it expects some arguments, right? It expects a context and a type, so we had better provide those here. So values, of course, in this, when we run well-typed terms, we need types on values as well. So let's do that. So this should be, value should take a type. So it's an indexed type, indexed on a type. Environment should also be typed now. So environment, an environment for a context gamma. But we did this in the evaluator before. So that's just n of gamma is for every name type pair in the context. So remember, a context that we had on Wednesday is a list of pairs of names and types. So we need a value for each type, so for each second component of that pair. Okay. And then we need to type our values. So what's the type of lit n? Well, it's a value of type nat. And so notice values are closed, of course. So there's no environment to worry about or context to worry about for the values. Yes.
So if I want to make sure from memory, you might want to stop and say that that's the composed.
Oh yeah. This is yes. This is function composition. So let me type it out. Well, we can do it like this. Okay. What's the type of successor? Well, it's nat arrow nat. And then we need to type closures. So we're going to need some stuff. Well, a closure has function type, so we'd better have some types A and B. We need a context for the term, context gamma. We'd better name that. So the environment is an environment over the context gamma. The value, we hope to get out a value from A to B, and then what should the term be? So the term is the body of the lambda, so we could just look up what type that had in the definition, but I'll just type it in here. So it's not just gamma, but the body, the type of it is B, but then it's in the extended environment, extended context where X is type A. Okay. So this is basically taking the typing we had on our terms and just writing down what that means on this value type where we have closures and stuff. Okay, so then there's this directive type. So what we were saying, okay, a directive is something that can operate on a stack of a certain height, and then it gives you back a stack of some other height. But now we want to actually, we want to have typed stacks, right? So we want to change this. We don't just want to keep track of, how many things there are on the stack. We want to keep track of, the types of the things on the stack. So I'm going to define a little synonym here, which is stack type. So what's the type of a stack? Well, it's just a list of types. One type for each element of the stack. And then we're going to index directives not by starting height and ending height, but by starting stack type and ending stack type. So we do that, and then it'll still complain about the same thing. So if we use delta for stack heights, this term. Okay, so what it's saying here is term. I just said term. I'd better give a context and a type for it. So what's the context going to be? Well, for directives, the context doesn't matter. So we can. Well, we need to have one, of course, but I can just put that up here as a parameter, a context gamma. We're going to need a type as well over here, and then n is inbound. Okay, so instead of n, I put delta. And now the question is, what's the final, after you've run the directive term, something with a term of type A, well, you had better put the value of type A on top of the stack, right? So rather than 1 plus n, we have A cons delta as the stack height. Didn't like that. Oh yeah, gamma, huh? You're right. Okay. And then the apply will work in the same way. So we had 2 plus n to 1 plus n. Well, now we're going to have to write down what the types of those two elements are supposed to be, and then what the type of this one extra element is going to be. So again, we're going to replace n by some arbitrary delta. We're going to have a type A and a type B. And then on the stack, we're going to expect, and now we have to remember the definition, did we have the function first or the argument first? I think we had the function on top of the stack and then the argument. So we're going to have a function from A to B, and then a value of type n, A, and then delta, and then let me not forget gamma this time. So if the stack looks like this, you have a function from A to B, and then you have an argument to that function, then you should be able to run the apply directive to get, in the end, once it finishes, something of type B on top of the stack. And the rest of the stack just stays the same, or the type stays the same at least. Okay? Then it's complaining about stacks. So stacks we had stacks as vectors, right, before when we kept track of the height. Well, now we're going to, it's not indexed by a natural number anymore. It's indexed by a stack type. So let me write out the type here. So delta for stack types. So what's a stack matching a stack type delta? Well, for every type in the delta, there should be a value of the corresponding type. So by now, I think you can see where this is going. So that's the all version of lists. So it says for all things in delta, we have a corresponding value. Yes?
Why are we putting gamma as an implicit parameter in the directive?
Because the terms on the terms in the control references variables of the environment, but the directive isn't manipulating the environment. So in here, no one's touching. Term doesn't touch the environment, and apply doesn't touch the environment. So I can just it's just the same gamma everywhere. And
Why don't we put it in curly brackets?
oh, make it implicit. Well, if I put it in curly brackets, then that means I'm not going to mention it when I say directive something. But it matters what the gamma is. So it's not going to. You won't be able to infer that when you talk about the type, right? Because later on, we're going to say in the snapshot here, we're going to say, okay, you have a control for some gamma, right? And then it's important which gamma the control is for. Okay, let me write out this type as well, stack type, to make this explicit. So a control, well, it's still going to be a path, right? So it will start at some stack type delta and go to, so why didn't this, oh yeah, okay, so actually we don't, we also need the context, of course. That's what it's complaining about. Okay, good. Right, so the only thing we had to do to control actually was to add gamma as an argument to directive. So it also takes this gamma now. But it doesn't change throughout the whole control. It's the same gamma everywhere. All the things on the control, all the variables in those terms, they reference the same, they live in the same context. Because every time we do something to the context, we're going to swap out, put some stuff on the dump. Okay, and so then we get some errors down here. So snapshot. Well, okay, so here we just have to change the natural number tracking the height to a stack type. So let's call this theta. The n is going to be a delta instead. The stack is going to be a stack of delta. The environment, okay, let's take that later. The control now is indexed by stack types rather than numbers. So here we should say, so J was the extra stuff that should go on the stack. Well, it's now an extra list of types that we expect on top of the stack. And then the delta. And then it should go down to a stack of height 1. Well, now we not only care about the height of the stack, we care about the types. So it had better go down to a singleton list of some A. What A? Well, we should probably put that as a parameter to the snapshot, because we're going to need that outside. So that just leaves the environment. Oh, and also the control. So we need a context as well, and that we can put in as an existential inside here. So this is fine for any context, as long as you match up the environment and the control. Everything is fine. All right, so we're making progress, and we're hoping in the end that we are doing the right thing. But we are so basically we're just changing. Mostly, we're changing the natural number to a stack type instead, a list of types, and we're adding in some extra type information. So the snapshot here now takes an A. So let's think about the dump, because this is maybe not obvious. So what are we using the dump for, right? So it's when you're about to apply, you want to apply some closure to a value that you've just computed. And that should then, you hope, come back with a type, some type A. And then you want to use that type and compute some other type B. So a snapshot, so what we do then is we put something on the dump, right? We say, okay, the thing I'm doing at the moment, I want the thing of type A, and then I'm going to compute a thing of type B. So the snapshot that we put on the stack, notice there's one here. So it expects one extra thing on the stack. That's something of type A, right? That's the thing we're about to compute. So that should be a singleton A. And then once it gets that, it should compute a B. So now this doesn't make sense because A and B aren't bound, and I'm making a list here. But this is basically, the things on the dump should look like this. So there's snapshots which expect an extra A on top of the stack, and if they get that, they compute something of type B. And now, what's the dump? Well, it's a sequence of these things that tail up these types. So the thing on top of the dump expects an A, computes a B. The next thing on the dump wants that B and will compute a C, and so on. That's exactly the path type that we had, yeah? So a dump, let me type this. So a dump from a type A to a type B. Well, okay, let me remove those. So a dump is a path of these guys that line up the types appropriately. So I'll put bind A and B inside here. So we're saying the dump tells you how to get from a value of some type A to a value of type B, and the way you do that is you run all the snapshots. So you take the first snapshot, it wants your first type A, You run that, you get the type A1. That's exactly what the next snapshot wants. So you pull that off, you run that, you get A2, which is what the third snapshot wants, and so on. And in the end, you end up with the type that you wanted in the first place. So we should be able to wrap this up. So we're going to type, a configuration of the SCCD machine. It's going to compute in the end something of type A, right? The current snapshot, so it doesn't expect anything extra on the stack, so that 0 is just an empty list now. What's the type of the current snapshot? Well, it's not A, not necessarily, because we might be deep in the middle of evaluating some closure, and we have a bunch of stuff that we want to do with the result of that. So this guy, the current snapshot could compute any type you like, as long as the dump tells us how to go from this type B down to the final type that we care about. So if the dump can take us from B to A, the current snapshot can compute a B, then we have a valid machine configuration that will compute something of type A. And so we just bind B here. For any B, this will do. Okay, let's go on. Okay, so step results are also typed now, of course. So step result A, you can either give a value of type A, that's fine, or you give a new machine, which will still compute an A, or you get an error and then you can do whatever you want. Down here, the step function, well, for any type, if you have a machine that can compute something of that type, well, you can run it in one step and you'll get a new, possibly a new configuration or a value or an error, but it's going to be of the right type. Okay. Now we have to change something, because remember we went from unchecked terms to type-checked, well-typed terms, and well-typed terms had the Brown indices instead of, they had the name, but also the Brown index. So it's complaining now that there are too few arguments to var, so it takes an index as well. And now it's saying, well, this doesn't work. Horribleness aside, all is not list. So we're trying to look up, use the list lookup function, but the environment is an all thing, and we have this the Brown index I, and actually we defined a function for this. So it should just be lookup in E of I, and then we run that, and it says no. What's this nothing thing here? That's not a value. Nothing is not a value. Okay, so I guess we have to get rid of this case. That's unfortunate. And then we just have this case, and then we can tidy this up a bit and just say, well, okay, just look up the value in the environment and put that on top of the stack. Parse error. Oh, yeah. Okay. So we have to change some more stuff here. So what is it saying here? Well, something you can't read. Let's look at what it's complaining about. It's when we're applying a closure, we're sticking something on top of the environment. And before we had an environment which was a pair of a name and a value, but now we've switched to de Bruijn, so it's just a list of values. So we just get rid of the X. Okay, and then we get down here, and it says A arrow B is not nat. So why would you try to apply a number to something? That doesn't make sense. Okay, so let's get rid of that. And it says, well, no, look here. Nat is not nat arrow nat. So you couldn't possibly apply successor to successor. That doesn't make sense. Well, we get rid of that. And then again, you know, nat is not A arrow B. So this doesn't make sense. And then we added a type here. So it'll either give us an error or a value of type A. And same here. For any A, we're going to run a closed term of type A and get back either a string or a value of type A. And yeah, this doesn't make sense anymore. Oh, and this also. Yeah. Oh, and it checks. So we're done, right? Well, almost. You notice all these cases we had here before that said error or something. They're gone. So why don't we take this guy out? And then, it complains, well, what is this error thing you're talking about? That doesn't make sense. It checks, well then, we can take out the either as well. And then the right. You are absolutely right. And there we are. Yes, absolutely. So how far? Yeah. Yes. So I think we have time. So if you want to take a moment, go through what we did again, that's perfectly. Right until. Oh, down here, yeah. Yeah, this one. So what we did, this was we had a lookup something, look up the variable name in the environment, and then it maybe it was there, maybe it wasn't. Well, now we have well-typed terms, right? There's a de Bruijn index up there, I, that tells us this variable is in the environment, and then our lookup function that we did the other day, it can't fail. You have an environment that has a thing for everything in the context. You have a de Bruijn index which tells you the variable is in the context, and so you can just look it up, you get back a value, and you go. That's fine. It doesn't like it.
So I tried to type like you type, but I have an error with Clojure.
Yeah, I get a weird error. Not implemented type checking of with application when checking the expression.
Oh yeah, \bar. Sorry, I'm sorry. This is Unicode bar, and you typed ASCII bar. That was a bad idea. \bar.
Backslash in the vertical bar.
Yeah. I apologize for that. It looks too nice to pass up. I don't know what other syntax. Yes. Yeah. Right. So that's an excellent question. Before, we were, it made sense. We had lambda that were really unchecked lambda terms. I could, write down lambda x applied to x applied to itself and run it in the machine, so it really didn't terminate. Now, though, we're running well-typed terms, and we know they terminate. Very bright people have proved that, which is why I don't want to do it. I trust that the simply typed lambda calculus is terminating, I wouldn't want to convince the termination checker that this particular way of evaluating simply typed lambda terms is terminating. That'd be hard. So let's not do that. And that's what I said in the beginning. We're gonna use dependent types to make things nice. We're not gonna aim for some full correctness of anything. Yes. Yes and no. So what you could do is, you're going to have an extra argument here, which is, so the termination checker does structural recursion. There's some size types you can do, but I'm not sure, that they would work. I think you probably need a more complicated measure for this. Yeah. So you'd basically you'd have to put an argument here which was clearly getting smaller. So there's you can do well-founded induction, and then you build up sort of you can basically build up the call graph or build up you have a well-founded relation and you prove that everything is getting smaller, and then you can do it. But it's going to be painful. And what's the point? We know that. So what we don't know here, you might be concerned that we got the machine wrong. We know we didn't get the types wrong. It's going to come back. When it comes back, if it comes back, it's going to come back with something of the right type. But there are many things of the right type. So maybe we made a mistake and we're computing the wrong thing, and it doesn't actually terminate. What you can do, it's a bit more painful than what we did now, but it works, is you can index the machine not just by the type, but by the semantics of the term. So you'd get the type up here. Well, I think the better to look down here. You say run takes a term t, and it gives you a value which represents eval of t. So with the eval function that you did in the exercises. So you can do this, and the same experience holds. So the step function would just go through unchanged, but there's a lot of more work to do in the types. But it's possible. So that's a hard exercise for you. So what's that? It can go on. Okay. So I don't have anything more to say, but if you want to go over some of this again, if things were a bit fast, then you can take questions. And then I want to say a bit at the end about next lecture. I will on Sunday. So I want you to go through this and try to do it yourself. And if you follow along now, excellent. But if you got stuck somewhere, sit down and try to do it. It will, and in fact, it is already on GitHub. But I did the summer school in France before coming here. So if you go to GitHub, there's a branch for solutions for that summer school. But I encourage you to sit down with this and sort of play with it and see what. Repeat what I did now. Okay, so just to reiterate what we did, So we had to think a bit, right? There were some cases where, like with the snapshots, where we had to add this extra theta parameter, or j as we called it first, where we had to think about what is the structure of the thing we put on the dump. What is, in this configuration, this is also an interesting thing. The current snapshot, it computes something of some arbitrary type. So there's some thinking to be done here, but it's all this thinking is just putting into Agda the invariants that you, if you really understand the SCD machine, already have in your head, right? And this is just explaining these things to the type checker. And what we get back from that is that we could get rid of all the boring error handling. The type checker just says, well, fine, these boring cases, the error cases, they're not going to happen. Just do your thing. So I think that's nice. Okay? No more questions? Yes?
Abstract machines like CESK or CEK that are, I think, even better than SCD.
Yeah. So I think this is because it's the most well-known, I guess.
Yeah, but you can do exactly the same thing.
I did CEK.
Yeah.
And it works out exactly right.
And then the other comment is you can do this in Coq, and it's really painful. So it may be worth showing sometime. What? Because I think this shows off exactly why Agda is great, right? In terms of programming these kinds of PCs.
So that's a good lead into my note about the next lecture. So I don't have anything particular.
For next lecture, I have a few things I can show you, but I also want you to think about topics that you might want to know more about, something we've done here that you'd like to be explained in more detail, or some other feature that you'd like to see. So the things I could show you is after Andrew's lecture, I hacked up red-black trees in Agda with all the invariants in place, and you write down, I get a few more cases than Andrew has in the definition, but I don't get 708 proof obligations. So there are no proofs in that, as I promised. I can also show you, I know I promised no proofs, but I can show you some proofs. So I can show you Greg's proof by reflection, how that works in Agda, which is also kind of neat. And then if you have any topics. So think about that for tomorrow, and then we'll make a list tomorrow in the beginning of the lecture and take votes on what to do. Okay, so thank you.